So now let's move back to lab number 4. And it's about the integrator and differentiator. Let's first talk about the Opamp integrator. Can anybody tell me, is this going to be an inverting amplifier or a non-inverting amplifier?
Would it be inverting because it'd be non-inverting because it's going to the positive side?
Non-inverting?
Yes.
I would call it as an inverting because, you know, this is a source and that goes into the negative guy, right? So this is an inverting amplifier. And we are just making a slight change. We are replacing this resistor to a capacitor. And this guy is called as the Opamp integrator circuit. And we're going to do this 3-step thing. Ideal assumption of the Opamp, and doing the KCL at the negative node, and finding all the current I's. Can anybody tell me, do you happen to remember this? What is the ideal assumption of the Opamps? It is the current that flows in to this Opamp is going to be 0, okay? And the voltage at these 2 points, V positive, is going to be same as V negative, okay? And this is only because since we have a negative feedback. Okay, so these 2 are the ideal assumptions that we are going to use for finding the governing equation. And then we do the KCL at the negative node, which is here, right? And we have to then define the currents for that. And this is kind of generally how I define. That's IF, and this guy is IS. So from the source, it's flowing in, and from the output, there's a feedback, the current flowing in, then there's a current that goes into this input node. And this KCL is what? It's flow in is equal to flow out, right? Flow in equal to flow out. So we can find the flow ins are IS plus IF. And that is going to be same as IN. These 2 currents are flowing in, and that guy is flowing out of it. And then the next step is to find these current values, I's, right? Which is this one here, that one, and that one. So IS, it's going to be just the Ohm's law. So VI minus V negative. The voltage difference from here to there, it's VI here and V negative there, right? That is going to be divided by RS. What about current that flows across here? We should be careful here. Across the capacitor, there's no Ohm's law anymore, right? We should use the capacitance value, so it's C dV dt. And that capacitance was CF, the feedback capacitance, so CF. And the voltage V here is going to be what? V out minus V negative. So the voltage across these 2 points, V out and V negative, that is going to be differentiated, and that is multiplied by your capacitance. And this V negative is actually going to be 0 because V negative is same as V positive based on this relationship, our ideal assumption. These 2 are the same. And this guy is connected to ground, right? So that's ground. So this guy is what? Is 0. So it's going to be CF ddt of V out. And we know that IN is 0 based on our assumption, right? So we got IN, IS, IF, so we can plug that into this equation, right? Just plug everything in. And if we do a little bit of math, it's dV out dt equals negative Rs Cf 1 Bi. And if we write this with respect to the output, then V out T0 minus 1 over RC, RSCF, integral Vn T dt. This is what you see as the output voltage of the circuit you have here. And you can clearly see your input is being integrated, and it is multiplied by some number, and it also has a flip over, right, negative sign. That is coming from the fact that this is an inverting amplifier. So inverting amplifier is upgraded to be a integrator, but still that negative flipping over of this inverting is still there. Okay. So how about we try an example together here. V out is proportional to the integral of your input. That's a very simple thing. And in this example, we assume this Rs was 10 kilo ohm and Cf was 1 microfarad. And your input voltage is a square wave, and this frequency was 100 hertz. So that means the period of this is going to be, period is 1 over your frequency in hertz, right? So that is 1 over 100, or it's 0.01 second, right? So here is 0.01 second. And your input voltage, Vi, is nothing but it's 2 and suddenly drops down to -2, and then it's suddenly 2 and -2 and 2 and -2. It's just that it's not a continuously going up and down and up and down, right? It's just 2 and suddenly it's -2. So we can model it as just 2 and -2. And it depends on the time range. When time is up to t divided by 2, and when your time is from here to there, it's going to be -2. When your time is 0 up to half of your period, it's going to be 2, like that. So since now we have 2 different intervals and 2 different values, we need to, do the math differently in each interval, right? And our V out is going to be V out of 0 minus 1 over RSCF integral times 0 up to t of Vn. And your Vn is what? Vn is 2 within that time interval. So it's going to be just 2 dt. So if we plug in all these values, RSCF, and get this thing. So how about we find Rs times Cf separately? So that is 10 kilo ohm, so 10 to the third, times Cf is 1 microfarad. So micro is 10 to the -6. That is going to be what? 10 e to the -3. So we can plug this guy in here. And what is going to be this integral value? That's 2t, right? This is 2t. So we assume time at 0, your output is 0, so this goes away. And if you plug this in there and you multiply like that, it's going to be -200t. And when V out at t equal half of the period, that is going to be -200 times half of the period. What's the half of the period? 0.01 divided by 2, right? And that is going to be -1. It's a simple math, right? So this is going to be equation of output voltage when your time is from 0 up to 2t. So within this range of time, your output is going to look like negative 200t. So it's negative 200t going down like that. And the value at this point, which is time equals t over 2, that is going to be negative 1. We just got that here. Okay, so we just found how your output voltage is going to look like if you had a square wave going in and it's only for this time period. Then how about we find for the next time period, which is from here to there, from t over 2 to 2, up to t. Then what you do is V out, your initial time is not anymore 0, but we are going to use the initial time, and then 1 over RSCF times t over 2 to t, and here is going to be negative 2 dt, because what we just did was we just wrote down this equation down here, and Vn is going to be negative 2 for this purple time frame, because you see your input is negative 2 in this period. So if we do a little bit of math, we actually found this guy up here, right? So that's negative 1 minus 1 plus 200t. I'll just leave this for you to do the math. And then this is negative 2 plus 200t. So for this time period, from half of your period to 1 period, your output is going to look like this. It has a slope of 200, but it is starting from the intercept of negative 2. You see? It's curved like that. It starts from negative 2, and it has a slope of 200. 200, intercept is negative 2, right? And what is actually going to happen is this is going to be repeated forever like that. So the important thing here is you have applied a square wave, but now what you're getting is a triangular wave or a sawtooth wave, right? So this is what we wanted to have. We wanted to have the integral of your input, okay? So it's slightly different from our previous cases. Our previous cases, we wanted to have, if you remember from here, if you are putting a sine wave going in, your output is going to be a sine wave too. Maybe just it's flipped over, depending on whether it's inverting or non-inverting. So if you have a square wave going in, square wave coming out, whatever random going in, same random thing is coming out, just the amplitude is changing. That's what we wanted to have as an amplifier. But now, don't get confused. We want to have the waveform change to another waveform. And the relationship from here, your input to the output, is this being integrated. Okay? So that's what we want to see from this kind of circuit. So if we move on to the next page, I showed you how to mathematically solve this thing to get the waveform coming out, but I value this is more important. You want to kind of guesstimate what's going to happen, right? You need to have those kind of gut feelings. I always emphasize those kind of things, because in the field, you're not going to have the numbers immediately. You just need to develop a gut feeling, and then from there you come up with a math and all that kind of analysis. So I just rewrote this equation again. Your output is negative 1 over RSCF times this integral. So qualitatively speaking, getting your output voltage can be done in 3 steps. First, you find the integral, then you flip the sign, then amplify by 1 over RS CF. That's this here. You integral, that's step number 1. Then you flip the sign, step number 2. Then you amplify, multiply that 1 over RC. Okay, so for this time period, from here to there, your input is just a straight line. You have Vn as a straight line. Then what should we do? First, you find the integral of this. What's the integral of a straight line? It's a ramp, right? So you have a ramp like this. That's step number 1. You get the integral. So your input was just as constant. What's the integral of a constant? It's a ramp, right? And then step number 2, you flip the sign. So you flip the sign over like this. And step number 3, this is what you got already. Maybe you want to amplify that. Amplifying here means your slope is changing, right? The slope of the ramp is getting steeper or getting flat, something like that, right? So this is going to change. That's step number 3. And actually, that's what you got. This was your input, and your output looked like what? Your output looked like a sawtooth thing, going down, up, and take a look. This part was just a straight line going down, just like what we guessed here. So a straight line, a constant, you find the integral, which is going to be a ramp, and then you flip the sign, and then you change the slope depending on the 1 over RSCF value. Maybe the slope is getting smaller or the slope is getting steeper. Okay, so by applying this kind of 3-step thing, you will be able to guesstimate what's going to happen in your output. If this were like a ramp going up, probably this will be like a a cubic thing, right? Ramp is linear, right? So you can guess whether it's a parabola like this or that, and then you can develop your thoughts process. So then, now let's start thinking about the frequency response. And for the frequency response, we will directly just use the impedance here. So this was the inverting amplifier, which is, right? And that is converted into a integrator, and this RS and RF is converted into RS and CF, right? And when we are doing this impedance analysis, we can just call this impedance ZS and impedance ZF of a capacitor. So replace R to Z's. So that means V out over V in is going to be negative ZF over ZS. RF, RS, ZF, ZS. That's it. And here we use, what's the impedance of a resistor? Anybody help tell me? It's same as your resistance. What about ZF? The impedance of this capacitor. That is 1 over J omega CF. So the impedance of a capacitor is 1 over J is the imaginary number, omega is your frequency in radian per second, and CF is your capacitance of this guy. Next step is you just plug these back in here. In other words, V out over Vn is going to be negative. ZF is 1 over J omega CF over ZS, which is RS. And that is going to be 1 J omega RS CF. So the frequency response, if you remember from the RC circuit, we use H, right? And H is nothing but V out over Vn magnitude, right? Or we call it transfer function, or sometimes just frequency response. So transfer function, frequency response, they are the same thing. And that is nothing but it's the output over input ratio. So we just found that output over input ratio, that is dependent on your frequency. Let me just write this down just in case. So omega is frequency in radian per second, right? And RS is your resistance, CF is your capacitance. In the next page, I just copied that here and wrote it down here again. And how about we think about how this is going to behave? So your output and input ratio is negative 1 J omega RC. And what if you had a DC input? This guy had an input that's just a straight line, like this. That's DC, right? And that means your omega is 0. So in that case, what's going to be the magnitude ratio of this guy, H omega, or your transfer function or the frequency response? Your omega here becomes 0. That means if you find the magnitude of that, this whole thing is 0 and this is just a number. So this is going to be infinite. And the opposite case, what if we had a input that is an AC voltage with a very high frequency? So your omega is going to be like infinite, and this is infinite here. Then what's going to be the magnitude ratio of your integrator? It's going to be 0, right? So if your input has a low frequency or a DC volt, then your output to input ratio is going to be infinite. So if you apply just 1 volt in there, you're going to have infinite coming out. And if you have the same amplitude, but that's an AC with a high frequency, then that means your input frequency is infinite, and your output amplitude is going to drop down to 0. So if we plot that in a Bode plot, that is in decibel scale, right? And we are looking at the output to input ratio, magnitude ratio, and log of your input frequency. Then this guy, for this here, it's going to look like a straight line going down like this. You can see in low frequency, when the frequency is low, that is almost like infinite, so it's a very large value. And when the frequency goes up, it goes towards 0. So it's dropping down like that. Actually, it's dropping down as a straight line. And because this is an infinite, in low frequency, that value is in the range of several hundred decibel. So that is actually a huge value. It's like more than 100 times or anything like that. But in reality, there's a problem with this. So DC or AC is a problem when you use this integrator circuit in real life. Since DC input, which has your frequency 0, makes ZF is 1 over j omega CF, that becomes infinite. So this guy here also becomes infinite, just like we wrote down here. And that's not possible at all. When you think about it, if you're getting like output amplitude infinite coming out, how can we have that? Things are going to blow up, right? So this is just mathematically it's working. In real life, this part is not going to work at all if your frequency is low. And also, your input current is not going to be 0. So even a very small difference in the input gets significantly amplified, then your Vout gets saturated to Vs positive or Vs negative. So you're not going to have your output as this huge, large number, but it's going to be saturated. So we need a slightly different configuration by adding a resistor and keeps the feedback loop. What I mean by keeping the feedback loop is this thing here. This ZF goes to infinite. That means the impedance of this guy goes to infinite. And infinite impedance, that's meaning your circuit is disconnected, right? That means this feedback loop is gone anymore. There's no feedback. That's a problem what we have here, okay? So if the input frequency is very low, like a DC volt, then your magnitude ratio is going to be infinite. But it's here, that's not going to happen because this thing gets infinite and your input current is 0, not 0, so it gets saturated. So the remedy for that is we would like to keep this feedback loop by having additional resistor like that. And that is so-called practical Opamp integrator.